The industry in recent years has had a chip design boom. Everybody and their grandson wants to design the best chips for their use cases. And we have lots of industry experts trying to design the next generation of silicon. Today, we're talking Tachyum and their universal processor, the Prodigy. They announced it in 2018, but in 2022, they've got so many updates, it doesn't look like the same thing. I'm joined with the guys from Chips and Cheese, and let us talk you through some slides we've put together about what this new Tachyum Prodigy processor looks like. What's your minimum specification? So joining me today are Chips and Cheese. If you're interested in detailed technical deep dive blogs about chip architecture, then head on over to chipsandcheese.com. I've kind of been helping them with some of the work they've been doing lately. And joining me today are the main writers of the Chips and Cheese blog. George Cosma is cheese and Chester Lamb is clam chowder. So hi guys, welcome to the channel. Hope you're doing well.
Hey.
And first of all, I kind of want to tell the audience all about Chips and Cheese. So as I mentioned, an online resource for deep dive technology. And the great thing is they're a collection of like-minded engineers. Some are students, some are in the industry, some are industry adjacent. It just reminds me of the original Anantech when I joined. Everybody involved had that kind of sort of architecture background. And the whole point about Chips and Cheese, as you know, these guys are too modest to talk about what they do sometimes, but they do a lot of performance profiling from microarchitecture details. They have an in-house benchmarking suite, a micro benchmark suite. It's free to read. They've got a community Discord server that you should absolutely join, and there's also a Patreon available. It's great to hang out with these guys. And how big is the community now? It's about 200, 250?
I think in the Discord there's over 300. Let's see.
It's
There are 326 members currently.
I mean, it's fun because obviously I've been in this industry for a little bit now, and your name comes up in some of those interesting talks, or at least the Chips and Cheese blog. So this was an opportunity in this discussion because I've worked with the Tachyum guys before when they announced back in 2018. And I wanted to get these guys in front of Tachyum so they can understand what's new about this architecture. So let's go straight into the Tachyum Prodigy 2022 architecture. And there are going to be two groups of people watching this video. People who know about what Tachyum did in 2018 and those who didn't. So from the start, let's just talk about Tachyum as a company and that 2018 product. So we spoke before recording this video. I'll take the introduction to Tachyum because I've worked with them before. Formed in 2016. It's a Slovakian-American startup. They've got bases in Europe and in North America. They're still privately funded, private VC funded. They've taken, according to Crunchbase, $42 million in Series B funding. They've got advisors from AMD and ARM. They're involved in Euro HPC projects. There was actually an announcement recently that they're now part of a new Euro HPC think tank. And their whole product offering is meant to be this Prodigy universal processor. A processor that is, by virtue of its name, universal. Does both high performance computing and AI and server. And I think the key point here is that initially they showcased that processor in 2018 with everybody had a load of question marks because it was wild claims and wild design ideas, 3x the performance of Xeon. Some of those claims have still borne through to today, but we're going to go through why I think we're more confident in some of those claims today than we were back then. And also with relation to the company, I also want to bring up the CEO, Dr. Radoslav Danilak. If you've been in the industry a while, you'll recognize his name. He has had decades of experience in high performance CPU and circuit and GPU design. I mean, you just look at what he's done before. He over 100 patents. He was the CTO of Sandforce when Sandforce made the first true SATA SSD controllers. They were the ones that really took the baton and ran with it, and that's why we have the SSD like performance that we have today. He used to be an x86 architect when we had more than 3 or 4 x86 licensees. He's architected 10 gigahertz DPUs at Wave Computing. He's been GPU and chipset architect at NVIDIA, CEO of Skyera. And I think what's important here is that every company, especially every startup that he's been involved with, they've all been purchased. It's very rare in this industry to have engineers who know about architecture but can also lead and also essentially get the companies that they create to either an IPO or a saleable state. You hear about so many companies kind of folding because they don't have a reasonable product. Rado here has a history of bringing products to market and then getting value out of them for the companies that ultimately buy them. So, and in terms of Tachyum, founded in 2016. Now let's start off with that 2018 Prodigy product. As I said, it's 2018. It was kind of announced at Hot Chips 2018. I remember getting a briefing beforehand. It seemed very kind of high pie in the sky. That presentation was eerily quiet, and everybody in the Q&A said, "What the f?" Essentially, this doesn't seem like it would be possible. But I'm going to let George here go through what that processor looked like back then so we can compare it to what the design of the Prodigy looks like today. George?
So back in 2018, Prodigy's original design was for 64 cores at 4 plus gigahertz, which quite ambitious. This was going to be taped out on TSMC's 7 nanometer process, around 290 millimeters squared, and it was going to originally have, if you guys remember, Itanium from 2 decades ago, but it had VLIW like bundles and was doing a lot of in order, and Tachyon, much like Itanium, is doing a lot of stuff in hardware in order. So that means that one instruction goes from the start to the beginning, and it can't pass anything. Essentially, think of it as a road. Car in front of you, car behind you. You can't pass. You just
Like
have to
like like
go with traffic,
train tracks.
like train tracks. And
So just to come back to this VLIW, very long instruction word. So normally when we think about a processor, it's one instruction, one piece of data, one operation. VLIW is you essentially pack 4 or 5 instructions into one instruction. Doesn't sound right. Into one bundle, and the processor processes bundles, not individual instructions. It's a way to increase throughput, but you end up with lots of if you end up with dependency, it's a pain. That's why Itanium failed, because it
yeah,
relied on the compiler to do the work.
and Tachyon is trying to get around that with essentially trying to use the compiler to get out of order throughput through decreasing those dependencies. Now, Itanium also tried this. Unfortunately, getting your compiler right is very, very difficult.
If I think I remember at the time, Rado said that Itanium was hardware first, compiler second, and the idea was this processor was meant to be compiler first, hardware second, the other way around. That was his justification.
Well, speaking to that, you can tell that in this original 2018 design, their L1 was very small, even by x86 standards, right?
Hmm.
16 kilobits for your L1I and L1D is half of what Zen 2 or Skylake has. And that 256 kilobyte L2 at the time was on par with Intel's client side Skylake, but was dwarfed by Zen and Intel's server Skylake L2s.
I mean that
Um,
that was the point. This chip wanted to do both server and HPC and when you've got caches that small, it doesn't help. They kind of wanted a impressive memory structure, though.
Yeah, their memory structure was 8 DDR5 channels along with 2 HBM channels. They weren't very specific on how wide their HBM channels are, but we assume that this was the not the cut down 512 stuff that Micron was talking about, but the full fat 1024-bit per channel, which would actually give it quite a good like memory
Sounds like
bandwidth.
Sapphire Rapids. Hmm.
Yes. Um, However, again, going back to that whole hardware second idea, they didn't have a lot of registers per core. They had very, very few at the time, which can very much impact just your capacity to hold data within the core. So you're going to have to go out to that already quite small L1 more often, and then out to the small L2. And even that
I,
32 meg L3 isn't that big for 64 cores.
I mean, even back then, I think a lot of the question marks on it were we already knew that if you want to feed the beast with HPC designs, you need wide, fast caches, and these were just really tiny compared
Yeah.
to what was being talked about. So,
And
I mean,
then again, speaking on feeding the beast, except more like feeding the things that are attached to the beast.
mm,
Um, you have two 400 gigabit NICs, which are quite interesting for an HPC chip to have those directly connected to what is nominally a vector processing unit. This is very
mm.
reminiscent of what Frontier did with its NICs and connecting the NICs directly to the GPU instead of through a switch to the CPU. However, for server, 72 PCIe 5 lanes is a bit small. I
This
think,
was announced. This was announced before PCI 5 was a thing as well.
yeah. And
So,
you had Zen, well, AMD Naples and AMD Rome from the time at 128 already.
mm.
Um, so that was not class leading, I would say. However, in 2019, they were planning on taping out in 2019. Sorry, in 2018, they were planning on taping out in 2019 with high volume manufacturing in um, 2020, I believe. So, some perspective on Prodigy 2018. Um, they were saying, so we already know that their process was TSMC's N7, same as the core dies on Epic Zen 2 server. And Intel, of course, was using 14 nanometer with what was then their newest processor of Cascade Lake, which was a Skylake derivative with a couple more instructions. Um, Now, TDP wise, Prodigy actually looks pretty good here, foreshadowing for what's coming later at 180 watts with Epic and Xeon at over 200. Um, and this has as many cores as Epic, and which means over double the core count of Xeon at the time. Its clock speed again looking very, very good. 4+ gigahertz blows Epic completely away and still quite handily beats Cascade Lake. And same for the vector units. Now, this can get a little bit weird with Epic because of the additional 2 FAD units, but just talking FMA here, double what AMD was doing and the same FMA throughput as Xeon.
So what happens with Prodigy is that it mostly tries to do things in order, except that the most expensive things for in-order processors, like cache misses, like you go out to memory, that takes hundreds of cycles. You don't want to be sitting there doing nothing. So a lot of in-order processors can actually move past a cache miss and execute some instructions ahead of that. The problem is when one of those instructions uses the result of the cache miss, it stops there. So 2018 Prodigy tries to avoid the bulk of that by being able to save a checkpoint when an instruction tries to use that result. It doesn't have to then stop at that instruction and spend 100 cycles there. So what it can do is save the state there, move on ahead. If anything goes wrong afterwards, it can use that state to recover. But it was really limited in what it could do. It could only save a single checkpoint. And yeah, it's not really the same level as what you would see from a full out-of-order processor. So I would call it partial out-of-order. It goes beyond what you would see from, say, an ARM Cortex-A55, but it definitely can't do everything that, say, Zen 2 or Skylake can. It can't, like, reorder past instruction dependencies. It can't pull instructions from multiple basic blocks across branches and issue them in parallel.
I mean, it was a design trade-off, right? In terms of power,
Yeah.
die area. I mean, you're trying to fit 64 cores into this 290 square millimeter chip, each core with two 512-bit FMA units. You've only got so much size to fit it all in, right?
And what gave here was a full hardware scheduler.
Speaking of that sort of design trade-offs, you can really see that in the branch predictor of 2018 Prodigy, and that it is a design that is reminiscent of something like K7 on AMD's side, which is ancient at this
2000 and 1990
1998, like 25 years ago.
It actually has an even smaller BTB than that.
The K7?
Yeah, K7 had a 2048 entry BTB, also tied to the L1i.
Yeah, so it's very much a older cache design. However, something that, again, is on Prodigy's side here was in 2018, its pipeline lengths and mispredict cycles was only 7 cycles. So if you mispredicted something, you only lost 7 cycles.
It's something.
Yeah, so for comparison, like, this is really going back in time here, because around that time, the late 1990s, early 2000s, you actually had out-of-order CPUs with pipeline lengths in that range. Like, I think K6 had a 6 to 7 cycle mispredict penalty. It went into, like, what, I think maybe 10-ish cycles for Athlon. But this is really, like, you have a branch predictor that's not particularly strong, even for that time, like, even for that early 2000s era, but you also have a mispredict penalty that's comparable. And of course, you're not trying to reorder, like, you're not going into hundreds of instructions in flight the way you see on Zen and Skylake. So you're not going to be throwing out all that work just because of a mispredict. So you're, like, losing a lot, but, like, you're also losing less because you're not trying to go as far, if that makes any sense.
When Rado came up on stage and presented this, it's that sort of, because nobody had time to digest it live. Everybody was taking the headliners, and with those presentations, you kind of have to take some of what they say at their word. Then everybody came out, had a couple of days to digest, and then that's when all the articles came out. But since then, I think it's important to hammer home that it's been 3 years. We never saw Prodigy tape out. Part of that was pandemic, part of that was other stuff. And there was still this question of whether the claims being made back then were still going to come to fruition. And it was, earlier this year? Rado came out and basically said, we're doing, it's sort of a similar design, but just a lot better. And there's been some major changes. And some people wrote about it, but I don't think they caught the essence. I mean, for my regular audience, it's you guys know that I speak to architects and engineers fairly regularly for some of the content I do. I reached out to Tachyum and got these guys on a call just so we could go through exactly what that new architecture is about. I mean, we'll talk about how that call was really fun and went on for twice as long as what was planned. But let's go over what the Prodigy looks like today. So ignore what you've read online. Everything online you read is wrong, unless you've read it at Chips and Cheese or you're watching this video. Chester, hit it.
Yeah, so today Prodigy is completely different, and part of that is at least thanks to, well, back then TSMC 7nm was the best you get, now it's 5nm. So with that, they've taken it from 64 cores to 128. So think of that as being comparable to Ampere Ultra Max or AMD's upcoming Bergamo CPU. They have multi-socket support. They probably did before, but that's worth mentioning. You could probably get 256 cores in a single node. They're running that at an utterly incredible 5.7 gigahertz. So we've seen AMD show it as Zen 4 can kind of get there, but they're almost certainly not getting there in a 128 core SKU.
I think it's only IBM that have shown that high frequency before in some of their Power 10s, right?
Yeah, I mean, IBM can get there, but they're not putting 128 cores on a single socket. They're not trying to
8
cool.
cores.
Yeah, they're not going for this incredible core count at that frequency, but Tachyum is. And to feed that, they put like an absolutely gigantic memory subsystem. So they have DDR5 now. This is faster DDR5 than you can probably go out and buy today, even on the consumer segment.
On the multi-socket support, it actually can support up to 4 CPUs on a 4-socket coherency, so 512 cores in a single.
I would love to see the Linux scheduler deal with 512 cores all visible.
I mean, the Linux scheduler already has to deal with Intel and its 8-socket craziness.
It's going to be even worse if you try to run Windows because of processor groups, and most apps are not supporting that. So
I remember doing an article a few years ago about Microsoft were doing glueless logic and did a 32-socket system with 28 core Skylakes. Yeah, 796 cores in a system, and in Task Manager as well. That was fun.
Yeah, you can address that many cores. Good luck getting applications that can support it and really scale out.
Yep.
But if you can do that,
sure.
If you're a cloud provider, maybe it'll work out for you. Maybe you can fit that much.
Go for it.
Node. Yeah.
You do you.
And then they're also trying to feed this with a giant memory subsystem, because if you have a lot of cores running that fast, you're probably going to pull a lot of bandwidth. So this is faster DDR5. DDR5 7200. If you go on Newegg today, well, just look at how much you're going to pay for it and how easy it is to buy that. And remember, this is consumer memory. Server memory usually tends to be a bit slower, so this is a pretty ridiculous setup. And they've got 16 channels of that. So, well, DDR5 channels. So let's just say 1024-bit.
So it's like having a stack of HBM, but there's actually no HBM on it this
time. Yeah, they've gone away from HBM, but this is the biggest DDR5 setup you could possibly imagine. This is giving you as much memory bandwidth as like a RTX 3090, but also server memory capacity, so hundreds of gigabytes. They're doing this on a somewhat larger die now, 500 millimeter square, not something that's totally out of whack though, on TSMC 5 nanometer, so that's a lot of transistors.
Compare that to H100, which is 800 plus millimeters squared on the same process. So very much within reason.
Pretty modest die size, considering what they're trying to do. They're mostly out of order now. Now, I'm actually kind of confused about this part. It seems like they can do everything that a full out-of-order CPU can. So they can reorder past all sorts of dependencies, including cache misses, including instruction dependencies. So that kind of implies a lot. They've ditched a whole VLIW thing, so they're no longer using bundles. They're using a more traditional ISA. Well, this is still a new ISA, but now it's running discrete instructions. They have much larger caches, so they have very nice 64 kilobyte L1 caches, a lot like Athlon. That was a very nice feature of Athlon. It's a match for, say, Neoverse N1, which also has 64 kilobyte L1 caches on instruction data side. They still have like about they have 1 megabyte of cache per core at the last level, which is not great. The standard today is kind of like 2 or more in the case of Epic. But at least if you're looking at a single core, it has a lot of cache because it can actually combine all of that into a virtual L3 pool. On the throughput front, they have gone absolutely nuts. So if you look at original Tachyum, they were doing A64FX or like Skylake X type vector throughput. Now they've doubled that, and they're clocking it even higher. So yeah, this is nuts. They've added matrix support too. Intel's probably going to do that with AMX, but Tachyum is doing that with their own method.
And they said there's no frequency decrease for when you're using these vector units either. So
yeah, you can think of what kind of power that might draw. Just foreshadowing for later.
Well, not just power, but also memory bandwidth. Some more foreshadowing.
Yes, I actually don't want to think about how much power you can draw with that kind of memory setup. But...
Yeah, just the memory setup alone, 400 watts.
Like previous Tachyum, they need to maintain some kind of compatibility. Just like we saw with Apple, you can't really pull off a transition without maintaining support for the most popular instruction set. So they're using QEMU to translate ARM and x86 binaries and they're hoping to use that to run those binaries on Prodigy, obviously with a performance penalty, but hopefully still fast enough that you can make a transition possible. They're hoping to sample in 2022, and as we noted before, this thing could possibly draw a crap ton of power, like with those giant vector units.
Over 900.
Yes, over 900. So, yeah.
We'll get to the SKU list later. Just stay tuned. Keep watching
Yeah.
for that.
So let's actually look at a bit of what Tachyon is packing into every single core. So at a high level, this is an extremely wide core running at 5.7 gigahertz. So you look at Zen 3, that's like basically a 6 wide core. We do have 8 wide cores today, like Apple's M1, running at 3.2 gigahertz. Now they're going to do this at 5.7. So this is something that we do not see anywhere else today on any process node. And they're pairing that with just
So ARM's using fixed length instructions. And the reason
yes.
why we don't necessarily see that is on x86 is because of the variable length instructions. This is a bit different.
Technically, if you look at the micro-op cache on Zen, that is 8 wide, but the rest of the core is not. You can actually sustain 8 instructions per clock on Zen because the renamer, the stage after that, is only 5 wide on Zen 1 and 2 and 6 wide on Zen 2. On Zen 3. So that's why I basically call them 5 or 6 wide cores. Apple actually has an 8 wide renamer. You can actually sustain 8 instructions per clock, but obviously you're not going to 5.7 gigahertz. Even on TSMC's 5 nanometer process. And Tachyum says they can. At least part of that, yeah, is probably due to their instruction set being quite simple. But
yeah. Now with AMD's Zen 4 coming out, which is also on TSMC's Zen 5, they're claiming well over 5.5 gigahertz.
The answer, as we're filming this, nothing's been unveiled yet.
True. But AMD did show over 5.5 in their Zen 4.
They showed one core at 5.5 gigahertz. I'll give you that.
True, but that does in some way validate a 5.7 isn't completely out of the realm of the insanity.
They're just pushing it a little bit.
Yeah.
Just a little bit with like much bigger vector units, a wider core, a lot more bandwidth going around.
Yeah, that's where you start having the questions there.
Yeah.
And looking at the core, you can see kind of improvements throughout the pipeline compared to previous Prodigy. So the branch predictor has seen some improvements. There is now a BTB size that matches the likes of Athlon, Goldmon Plus. It's now 2048 entries, still coupled to the L1 instruction cache. You go to the address translation side, they now have we don't know actually what they did with 2018 Prodigy, but we do know that the 2022 version has a much bigger L2 TLB, so it can cover a lot more scattered memory accesses without incurring translation penalties.
And they're also using much bigger pages as well, which helps.
Yes, they're using larger page sizes than what you would see from ARM and x86. I think, what was it like? The regular pages are 64 kilobytes, right? And then the large pages
64
are
and 2 meg.
Yes.
Or something.
I think
they're 64 and 32 meg.
Yeah, so it's basically quadruple what you would see from... Actually, not quadruple. It is 8 times what you would see from x86 and ARM, where you would have 4K normal pages and then 2 megabyte large pages.
Isn't that 16 times?
Something like that. Something
ridiculous. Yeah.
Check the article on chipsandcheese.com.
And then everywhere else, it's still going to be much bigger than what you would see from any CPU today. Like they have low store bandwidth to feed those vector units. This L1 cache bandwidth is going to be twice what you see from like Skylake X per cycle, running at 5.7 gigahertz. So it's absolutely massive.
Twice per clock, 2x per clock, and then almost a 2x clock
too.
Yeah.
And if you look a little bit deeper, there are also various improvements that make this a lot more compelling than the original Prodigy. Like they have a lot more memory level parallelism, so they can actually sustain higher bandwidth from each core. Like if you look at the number of outstanding cache misses they can track from L1 and L2, It's now roughly comparable to like Golden Cove or Zen 3. Like you can track 16 L1 data cache misses. I think you can track like what well over 20 on Zen variants, but that's an equal to what Intel can track. At L2, well, Golden Cove can track like 48 misses to L2. I think AMD can track a lot more than that, but I'm not really sure because I'm basically playing with undocumented performance counters to guess at that, and I don't want to like make any firm statements. But
There's
I
plenty of
think they'll get
those.
more. Yeah, you can track 256 instructions in flight, and unlike the original Prodigy, you can keep multiple checkpoints in flight. So the reason they have not just 32 registers is so whenever they miss cache and if they save state, they can do that multiple times. So they can keep multiple cache misses in flight and keep renaming the registers, and be able to recover in case anything goes wrong.
Previous generation was only what they could only track one checkpoint. Now,
Yeah,
I
it was a
didn't
similar
Rado say they can track enough checkpoints that it's not an issue for practically every workload.
Yeah, at least according to them. According to whatever they've simulated, it is enough for pretty much all workloads, including ones where you're trying to sustain a lot of bandwidth.
It's they've already got these processors in FPGA design development that they're handing out to partners. Just to be clear, that still waiting on silicon tape out, I think. But yeah, no, this has all been simulated, emulated, all that jazz. So.
And let's quickly take a look at the ISA a bit because that's kind of pretty important here. This is a new ISA. From 2018 to 2022, they have ditched the whole bundle setup. So this is no longer something like AMD's Terascale or Tanium, where you could take in a bundle of instructions and be able to decode that a lot more easily than you would discrete instructions. Because with the bundles, you can do a lot of things like say, position 1 has to contain a certain kind of instruction. That decoder, that position can be a lot simpler and so on. Well, now it's discrete instructions. So it's a lot more like a conventional ISA, a lot more like x86 or ARM. And they did that because when you do bundles, the bundles are kind of tied very closely to the hardware implementation. So if you look at Itanium, for example, those are bundles of 3 instructions each. It could pull in 2 bundles at a time. Those bundles were mapped very specifically to the execution unit layout in Itanium. So that's why you see from initial Itanium to like later iterations, all the way until they totally ditched that and went out of order with Itanium, which is kind of funny, they had a very similar execution unit layout because they had very simple dispersal logic.
I mean, it's the sort of architecture you see in digital signal processors, or we used to have it in GPUs, right? And
Yeah,
if GPUs are anything to go by, every generation you essentially get a brand new architecture because you have to, because it's just not forward compatible.
yeah, they are tying the ISA very closely to the hardware. So Tachyum did a bit of talking around, realized they could not do that because in this world, if you're transitioning from one instruction set to another, that's actually a really big deal. It can take like 12 months to pull off, apparently, for a company to transition a big software project. Like from something from like x86 to ARM, that is. Adding ARM support, and ARM is already a very mature ISA. Like there's a lot of libraries around. Adding ARM support to a project, there's a good chance that what you need is there. Like that's not to say everything will be there, but there's a good chance that it will be. Tachyum realized that, or Tachyum's customers realized that, dude, you cannot change the ISA with every generation. If we're upgrading processors, we have to be able to swap out those servers, and it needs to just work. We cannot spend 18 months just to support a new generation of servers.
Especially if you want to update frequently. I think if it was a single DSP, like a modem that went into millions of units, it'd be fine. But because it's meant to be a high performance processor,
Yeah, with CPUs, it's a different world. Yeah, so with GPUs, you can ship a different driver. Driver is basically a compiler. You never talk to the device directly. So AMD or NVIDIA can change up an instruction set every single generation, and it's fine. Your games will run as long as they get the drivers right, which by and large they have been doing, despite all the flack they've been getting. Now, Tachyum can't do that with CPU, so now we see an instruction set that is designed to be forward compatible. So it's discrete instructions. Whenever the new Tachyum comes out, this instruction set should keep working. It should be backward compatible.
does this ISA have a name? Because obviously we have x86 ARM RISC-V.
No.
Is this just Tachyum ISA?
Yeah, I don't know. We'll just call it Tachyum ISA because I don't think there's
We
any other
forgot to
name out
ask.
there.
Yeah.
Maybe it's the Prodigy ISA?
Sure, yeah, since that's the only CPU that supports it right now, may as well call it that.
But in the way that x86 is variable length instructions from 1 byte to 15 bytes, ARM is fixed length. This is like RISC-V. You got two different lengths of instructions, so you get a bit of a trade-off of both.
Yeah, it's actually kind of similar to, I think GCN also has a similar layout where it's variable length, but only in certain increments. So it's not going to be quite as hard to decode in parallel as x86, where you have to figure out whether an instruction length is anything between like 1 byte to like 15 bytes. This can only have
Yeah,
two lengths. It's not going to be as easy to decode in parallel as like ARM, where you know, oh, I add 4, that's the next instruction. Add 4 bytes, that's the next instruction. But it's still probably like, because this is a fresh ISA, it's probably easy to decode in the sense that it's still very closely tied to the hardware and it's still going to be very simple. So if you look at what Jim Keller said, if I was going to design a new CPU today and I can pick an ISA, it's going to be easiest to use RISC-V because it is the simplest one. It's brand new, has no legacy.
it's no chaff, lightweight. I think he said 80% of all the opcodes used today are, or 6 opcodes is 80% of the code today.
Yes, and we can
So
actually show some statistics from, well, profiling x86 applications. That is often the case. Your most common opcodes
yeah.
are simple integer ones. I mean, there are
Mm.
exceptions, but in like general integer applications, they are. So the other thing about decoding, like instruction length is just one part of decoding. The other part is figuring out what the instruction actually does. And for that part of decode, Tachyum probably can do it very simply too, because this is a new ISA that is probably very similar. Like the instructions are probably very similar, if not identical, to the internal microops.
I mean, people always talk about one-to-one with instruction and microops, and the more one-to-one you can get, the easier it is. So
Yeah, the less translation you have to do. Like both x86 and ARM do all these things like micro-op caches, pre-decode, splitting one instruction into multiple instructions, just so that their backend can be very different from the actual
cracking
ISA.
and fusion.
Yeah,
Yeah.
and Tachyum, they haven't said anything about this, but I'm guessing that they are doing very little of it, if at all. So that's probably the decoder
Save
part
the die
is,
area.
yeah, the decoder part is likely not a problem getting up to 8 per cycle at 5.7 gigahertz. Zen 4 is probably doing it already. It's probably, maybe at a stretch, it could be very similar to even fetching from micro-op cache. We often hear this talk about how a processor is like in order or out of order. Like if you look at ARM, for example, Cortex A53 and A55 are well known as, quote, in order, even though they're not actually fully in order. And then CPUs above that, like for example, the Neoverse N1, you have Zen desktop CPUs, whatever, Intel X Lake desktop CPUs, those are fully out of order, so they can reorder past anything. But there's really a kind of spectrum. Like there's no black and white here. There's a spectrum between fully in order and fully out of order. And there's pretty much no fully in order in any consumer CPUs today. Like if you go back to the
It'd just be
486,
too
maybe.
slow.
Yeah, because if you're stalling on any long latency instruction and just stopping there, that's terrible for performance, especially because now there's such a huge gap between CPU performance and memory speed, especially memory latency. You stall for 300 cycles doing nothing. Nobody really wants to do that.
Yeah.
So we have even very simple low power CPUs like Cortex A55. What they're able to do is if they miss cache, they're like, okay, yeah, sucks. I'm going to keep going as long as I can and possibly finish instructions out of order. So have instructions finished before the cache miss comes back. And I'm only going to stop if I hit an instruction that actually tries to use that result, because now I actually can't execute it. I can't even start executing it. So I stall there. So that's good for maybe getting, I don't know, at most a dozen instructions past the cache miss. You're still going to be stalling a lot, which is why you see these in-order CPUs, even though they can kind of get past those longest latency instructions, they're not getting anywhere near out of order performance. So even in like 1994, you have giant IPC gaps between in-order CPUs and out-of-order CPUs, and that continues to hold true today.
But to go to out of order, it costs a lot in die area, in transistors, in power, and ultimately also frequency. So if it is a spectrum, you need to find the right form on that spectrum that gives you the best set of features and requirements for your product. Now, most of what we talk about in modern HPC, modern high performance, even in modern high performance mobile, is right in the heavily towards the out of order side. Prodigy 2022 is kind of in the middle.
I mean, over the past 2 decades, this trade-off has been happening. Even like in 1994, it was iffy, right? You could clock a lot higher with in order and actually win out of an out of order design. But increasingly, like we've been hitting this frequency. I mean, we've been hearing a story about hitting a frequency wall for the better part of the last decade now, right? So increasingly, we've gotten performance through higher IPC, more and more aggressive out of order designs that have more reordering capacity. They're wider. They take a lot more transistors. They don't really clock much higher, even with process node improvements, but that's where we're getting most of our improvements. So now we get to Prodigy, and pinpointing exactly where it sits on the spectrum is hard. So the 2018 one is probably one where they could save I don't know if you've heard of this obscure like research thing in like ICFP, in order continual flow pipeline, but at least what Dano described to us on the call, it seemed very similar to that. So they can save a checkpoint, and then when a cache miss comes back, they can rally from that checkpoint, run through all the dependent instructions from there, and with that, you're able to avoid the worst of the penalties from in-order execution. So your variables, that's actually what I believe Daniel was talking about at Hot Chips, when we were saying we did the stuff that a compiler couldn't do in hardware. I think that was referring to long latency loads, because the compiler can't really guess, like, is this load going to hit cache? Is it going to take 4 cycles? Is it going to take 40 cycles or 400 cycles? It doesn't know that. It can't really, it's very hard for it to plan ahead. So that kind of stuff they put into hardware, and then the other stuff, like kind of reordering instructions to get around dependencies, they were like, we're going to try to do that in the compiler, try to save that hardware. Because
this was a 2018 product.
Yes. Because once you try to do that full out of order scheduling in hardware, once you're trying to, in a single cycle, examine like dozens of instructions, let's say you have a 20 entry scheduler, every cycle you're potentially checking all 20 of those entries to see if they're ready to execute. And you can kind of see, if you're trying to do that much per cycle, that's going to cost you in terms of frequency. It's going to cost you in terms of die area, possibly both. So they were trying to avoid that. And we were wondering, did they keep the same scheme in 2022? And at least from our discussions with them, it doesn't seem like it. They very clearly stated we can reorder past simple instruction dependencies. So if you look at that figure there, they can reorder past very simple non-cache miss instruction dependencies. And that kind of seems like if they can do that, they can do just about everything an out-of-order CPU can do. I don't know if they're using an expensive scheduler. If they're trying to hit 5.7 gigahertz with the kind of die area that they have, I don't know if they're doing that. So
I mean, this is why you've got a question mark saying magic on your slide.
Yeah, so this is a magic execution engine. It can probably, maybe has a small scheduler. Maybe that's what they're referring to. But it can do everything that out-of-order CPU can, pretty much without paying the die area penalty, which is going to be funny to see.
It ultimately trades off with IPC at the end as well.
Yes. Of course, you could design a very small out-of-order engine. You can still get a lot of the benefits. Like, as you increase these structure sizes and you get more and more instructions reordered and do wider and wider execution, it's really diminishing trade-offs. So if you go from 4 to 8 wide, I think he said that gave him about a 7% performance boost in most integer applications. Just from playing a round of simulators like ChampSim or Gem5, if you go from if you double reorder buffer size, you get maybe 10-15% performance improvement, because you don't really use that long tail of reordering capacity, if that makes any sense, all that often.
It's always with when you update process design. Okay, you double this, you increase that, and you get 1% here, 1% here, 1% here, 2% here, and then it's the cumulative that it's the Japanese way of doing things.
But even if you have a very small reordering capacity, if they can do this full out of order, like everything that an out of order execution engine can do, we can expect pretty reasonably good IPC. Like, it's probably not going to match what you get from a desktop CPU or like Xeon or Epic. But the other factor, of course, IPC is one thing, 5.7 gigahertz is the other thing. This is clocking miles above any server CPU today. Let's just put it that way.
Frequency is the tide that raises all boats.
Yeah.
Unless your memory is too slow.
So you could have a tiny out-of-order execution engine that is 50% behind in IPC. If you're clocking 50% higher, then who cares, right? You're getting to the same thing at the end of the day.
Comes back down to power, but I think we'll get on to power. So if we just speak in terms of the compute throughput. I mean, whenever we see the high end products of the day, CPU or GPU, it's always, well, what can they throughput? Are we talking AI instructions? Are we talking HPC?
Yeah, that speaks to the kind of execution units they have. Yeah.
Yeah, so I mean, you guys done the math. It's the vector length engines times by frequency, number of cores. When you've got 128 cores running 2024-bit vector engines at 5.7 gigahertz, you get something really competitive for standard HPC workloads. I mean, we've got two graphs here showing FP64. Radeon Instinct MI250X is a dual GPU design, so that's just two GPUs anyway. And Prodigy is saying that they can essentially match that with just one 500 square millimeter monolithic at the peak frequency.
Imagine if this is like having a GPU, you have to throughput over GPU, but imagine being able to run a single threaded program on your GPU and actually get the same performance you get from your CPU. This is what they're claiming. That's how incredible it is. It can do CPU things, it can reorder past all kinds of stuff, it can do branch prediction, the kind of stuff that GPUs make a trade-off for in order to pack that kind of throughput in and still not explode their power budget. This thing is doing everything.
So you're saying I can run Crisis in CPU mode faster than I can in GPU mode?
Yes, of course you don't get all the fixed function hardware, but like if they added a bit of like texturing units and like geometry engines to this thing, yes, you could probably run Crisis on it fairly well.
If I said the word Larrabee.
This is what Larrabee wanted to be, yes.
So let's just throw that out there. We've also got the the 32-bit floating point vector units, and it smashes everything out of the water there. Though the important thing I think is we touched on it earlier. That you need to provide enough data to the cores to provide it for work. I mean, there's no point having a very detailed reorder pipeline or checkpointing pipeline if the data isn't there. And this is a graph. When you guys first showed me this, I was very WTF because the metric you guys have got here, it's DRAM bytes per 64-bit floating point operation, which is like a second order raw metric. It's not a calculated. It's not a real world metric.
FP64 number, that's 8 bytes, right? 64 bits is 8 bytes. If you're adding two FP64 numbers, you need 16 bytes to come in from somewhere, right?
Yeah.
If you're doing even more than that, like a fuse multiply add, you need 3 inputs. So you can kind of see how everyone is actually very bandwidth starved. If you do not hit cache, if you're pulling everything from memory, you're going to be limited just by how much data you can pull in.
It's when I first started programming GPUs back in 2010, it was always a case of, because you're dealing with kernels with multiple loops, and you've only got say 28 registers that you can put data into. You need to be able to produce around 30 flops of compute on the data you have in registers for every time you bring a new data point into those registers, if you wanted maximum throughput. That was where your bandwidth limited versus compute limited was back then. Over time, it's gotten a lot better because now we have more registers per CUDA core on an NVIDIA GPU, higher bandwidth, better interconnect. With Prodigy, we're kind of going back a bit. Even with 16 channels of DDR5 7200, the amount of bytes you can bring in per compute, per flop, it's half of what's there in the market, really, isn't it?
I would actually say it's continuing a long trend of being more and more bandwidth bound. So if you go back to like, I don't know, ancient days, where you didn't need cache because you had enough memory bandwidth.
Cinebench.
Not even Cinebench. I'm talking like before, like, I mean, 1980s stuff, right? You didn't need cache because your memory was fast enough.
Dry stone, that stuff.
So,
V-Ray just fits in L1
back to
cache.
those days, yeah. So like, say, I don't know, like a 486, for example, you had very little cache because memory, the gap between processing power and memory speed wasn't really that big. It's getting bigger and bigger. DRAM manufacturers, I don't like them. They've not been keeping up with how fast CPUs and GPUs have been pushing compute power. The
They
thing
don't
with
like you
Prodigy,
either.
yeah, okay. I guess you don't because I'm paying a lot for DRAM, yes. But Prodigy kind of pushes that, like, that's just one step further. And they are so much more memory bandwidth bound than pretty much everything else out there. Like, they're going to have a lot of trouble feeding this. That's not necessarily a problem because over the past couple decades, everyone has been dealing with this by stacking on cache. They've been doing caching better. But I'm not really convinced that that's there. Like, the amount of cache you have per core is less than Epic, less than Xeon. So they actually
And
do need to lean on this memory bandwidth a bit.
well, I mean, CXL was kind of meant to address some of this, but Prodigy doesn't support CXL, or at least this version doesn't yet.
Yeah, CXL, I guess you could pull in some more bandwidth from like a remote memory pool. That's not really going to alleviate this. It's not going to change the
Yeah,
ratio much.
Yeah, because
it depends how it's connected as well. CXL is still so in its infancy, and I think they can do a lot with it, but
And where are
it
you
is
going to
what it
connect
is.
it? You've used all 16 of your DDR5 interfaces. I mean, you can start gobbling up your PCIe links. That's where you're going to connect your CXL cards and stuff. I don't know how much further you're going to go on this.
Tachyum doesn't even have a lot of spare there
Yeah, they
for
don't.
PCIe lanes. They only have 64 in their new design. So that doesn't get you much even there.
These guys are still focusing on this generation products. They probably have a roadmap. It'd be interesting to see what they're doing to solve this as we go forward. I mean, they did mention a couple of things to us to help with the bandwidth, because I mean, when we talk
Yeah.
about DDR5 7200, we speak about it in the way we've always thought about memory. They're doing things here like changing the ECC granularity to 1024-bit, if I remember
Yeah,
correctly.
they're
So that
using
gives
larger
them,
cache lines. So usually CPUs today, they use 64-byte cache lines. So when you make a request in memory, you want to fill a whole cache line, you fill it at 64 bytes. They're doing it 128 bytes at a time. And they're actually
yep,
playing tricks with the memory controller. So you know how an ECC DIMM actually has 72 bits instead of 64
yep.
for data? And they actually have it. If you look at the model, you can actually see an extra chip sitting there, an extra DRAM chip. That doesn't actually help you with bandwidth because that chip is purely used to store error correction data. But by widening that ECC granularity, they're able to use less ECC data, and they're actually expanding the bus width a bit past what you would expect. It's not 64 bits. It's going to be somewhere between 64 and 72, depending on how exactly they're doing ECC.
So instead of 1024-bit, we should think of this more of like an 1100,
Yeah,
1120-bit.
they're pushing it. Yes, I don't know what 72 times 16 is. It's going to be less than that, of course, but it's effectively going to be a bit above that 1024. So that's yeah, and that's what you can do with custom memory controllers.
Rado also mentioned memory compression techniques and differential data reporting, where you only move out into main memory the difference between two values rather than the actual value itself. That saves some bandwidth. That's going to be very. I think at the end of the day, that's going to be very program dependent as well.
They've looked at some AI applications and how exactly the data tends to look like, and they've optimized compression for those really memory bandwidth hungry applications. But yeah, that remains to be seen. I mean, Dano should know how to do this. He's done it before with Sandforce. That used compression of some sort.
Yeah, if anybody knows it, it's probably him. But yeah, so just to wrap this up before we move on to onto the SKU list, single thread performance. We mentioned earlier, IPC is given the architecture, it's not going to be the best. It's going to be around that mark, but they're supplementing that with a super high frequency. It monolithic, 500 square millimeters. Core count matching the top generations that are coming out this year, next year, which makes you wonder. We've spoken about HPC and stuff with the Tachyum processor. Maybe it might be better suited for cloud, where the memory bandwidth doesn't matter so much.
Yeah, you mentioned that in cloud applications, integer applications, you tend to not need that much bandwidth, which is true. I mean, you actually see that with, if you look at the memory bandwidth counters and you do regular stuff day to day, you're generally not memory bandwidth bound. So it could work in cloud. They do have a lot of cores, a lot of compute density. If you can cool it, I mean,
George, take us through the SKU list because I know you've got very strong opinions here.
So, speaking on power, Tachyum's top level Prodigy SKU, their 128 cores at 5.7 gigahertz, is going to consume 950 watts, which is not a small amount of power consumption, even for in the server realm.
It sounds like you need a 1 horsepower chiller.
Yes, little 1 horsepower chiller under the table. I wonder who did that at CES before. Intel.
Now that's probably when you're hitting all the vector units, but like if you have a CPU that's spec'd to a certain TDP, you need to have a cooler for that TDP, or else you're gonna risk throttling. And even if you're in a cloud environment where, say, you don't expect everyone to be slamming those vector units, you need to prepare for that worst case contingency, because if somebody does, you can't tell everyone else, hey, I'm downclocking now, I'm throttling.
What's interesting on that downclocking thing is that if I remember the golem.de article, they were actually saying how they don't downclock, they just increase their duty cycle. So you wouldn't actually see a clock difference, but you would see decreased performance because it can just not issue an instruction if you're overheating or drawing too much power.
If any of you remember how Pentium 4 throttled, it's that.
I mean, it's TSMC has published research. I've got a video on it. How we can cool processors that are approaching 1 kilowatt and higher. TSMC did the research that if you actually put grooves into the processor and then do direct die liquid cooling with chilled water or chilled liquid, I can't remember if they use water or something non-conductive, but they could do 2.6 kilowatts. So that's not that crazy. That being said, one of the things with this chip is they're going for also density. So you can imagine 4 of these in a 1U requiring cooling. It should point out here on the SKU list, it goes from 180 at the bottom all the way up to 950. It's only the top 2 or 3 SKUs that are designed for HPC. So high performance computing, we're talking about, big nuclear models. But those are also the ones that are only spec'd to DDR5 7200. And when we spoke to Rado, he said when they coming out with this, they don't expect 7200 to be available in the market. JDEC specifications and support on that. They expect the HPC customers to go and buy 6400 and then bin it themselves to do 7200. They already do this with like the 600 watt GPUs anyway. So it's and then going down, it's actually the 300 watt SKUs. You've only got one that does 16 channel, the rest do 8 channel. I've also noticed that the 8 channels only do 32 lanes of PCIe Gen 5. That's going to be a limitation, I think. But these guys do have customers who are engaged. Like I said, they're part of the Euro HPC project. And with these startups, they do tend to build their first generation products for their main clients, because the clients are one that will probably spend a couple million or more. So they're going to be optimizing for that. So while it's a universal processor, memory access is focused on AI, but still, pivoting towards the HPC. And yeah, talking about this software ecosystem, I mean, for this emulation, we've seen bad takes on emulation so far. They want to do x86, RISC-V, and ARM. Actually, that reminds me, part of that is to do with but part of that is to do with memory modes. They're actually allowing strict ordering, aren't they?
Yeah. So much like how Apple's handling Rosetta translation for M1, you might have noticed that while you take a heavy penalty for Rosetta, it's not like you won't just drop through the floor and pretty much have it be unusable. That's because there's actually a lot of tricks that they've done with Rosetta. Like, for example, what x86 requires is, this is actually really hard to explain, but stores across CPUs have to appear in order. So if I write a value to one place in memory and I write a second value, on any other CPU core, I have to observe those accesses in order. Now, ARM doesn't require that. RISC-V doesn't require that. But that's something you have to take care of when you're dealing with x86 binaries, because it could so happen that someone has decided to avoid locks and go faster by taking advantage of this particular feature. So what Tachyum has done is they have actually implemented that too. So they can switch that on and assist that emulation. Now, is that going to give that good enough performance? I don't know, because they're translating of QEMU. QEMU, like, you can actually try this. Like, take an x86 machine or ARM machine, go run a mismatched binary through QEMU, you will see like a 90% performance hit. So
I
yeah,
think Rado said 40%.
yeah.
They're
So
aiming
that's
for about
really
40%.
in line with what you see with like Apple and Rosetta, right? Like a heavy, but something you can
Apple
stand,
has
at least.
tens of thousands of employees.
Right.
Yeah,
Apple is as rich as a software company, but they're also doing hardware.
yeah.
Yeah. I mean, we've got a final slide here. This is just sort of general chit chat. The fact is, it's ambitious, right?
Extremely. Yes.
I think ambitious is an understatement. I think it's
But that being said, I think based on the 2018 Prodigy and the 2022 Prodigy, after speaking with Rado for the meeting was booked for an hour and we spoke for more than 2. He was happy to go on. It's a lot more confident with the design now. Now that it's kind of been laid out a lot more clearer for us.
Yeah,
I
and you
mean,
can
still
kind of
lofty
see,
goals, but more confident.
you can kind of see how they're aiming to get there too. Like,
Mm.
it makes sense that you're pulling a lot of power to do what a GPU can along with what a CPU can, right? But then you also have the things like, all this stuff is intrinsically hard. Like, you see companies all the time screw this up. Like, you have Cavium develop a not too ambitious ARM server CPU, and then they had bugs when it came out. Like, they had some serious show-stopping bugs. And even more experienced companies like Intel or AMD, you dig deep enough, you're going to find errata. Like, sometimes they'll release chips that
the K10 BIOS ROM not being loaded. That was just
Or you have the mercurial cores issue where one core in a million gets a file size wrong and it screws up your entire system.
yeah, it's just like it's hard, and they're a small company.
I have calls with investors and Wall Street, and they're talking about all the cloud providers now building up their chip design teams to custom design something in house what they need, and I have to keep telling them, look, even if you get all the IP from ARM, if you get the cores, you get the interconnect, and then you just slap it together like it was Lego bricks, it's easy to do that, but it's easy to do it badly. If you want to do it well, if you want to actually get leading performance or leading power efficiency, if you want it to work first time, or at least at the very least second time, you need experts to do it. You can't simply just take people who want to be chip engineers off the street. It's helpful to have people who have experience in delivering products, and like I said, back Rado with high frequency silicon. And I have to tell investors, look, these cloud providers can design all they want, but if they don't have the right people, they're not going to beat what's already out in the market.
And we're talking about this thing just working in the first place. Like, is it actually going to hit their clock targets?
Do you understand what processor validation looks like?
Yeah, it's
right.
People write papers on this stuff.
And there are conferences, and the rabbit hole is very deep. Because there's no point driving a high frequency if you can't even get simple calculations right, or you have to.
Or if you have a bug that lets one user lock up a whole CPU, right?
I remember there was a CPU with a bug that required a cache flush every 32 instructions or something because of something going wrong. A counter going wrong or something, so they needed a cache flush every 32 instructions, and that just means you're going from your performance tanks. Okay, you get your 4 gigahertz or whatever, but there's no point because your duty cycle means that you're actually running effective 200 megahertz or something.
Yeah, but
So
at least from my view here, the risk here is enormous because you are targeting top of the line or higher clock speeds.
mm,
People will I mean, you could very easily release a CPU, realize that most of your bins cannot actually hit that clock and run correctly. Um, and then you're doing your complex reordering in hardware, so that a lot of things can go wrong there as well. And then they're a small company, right? So even if you have a lot of experts make mistakes too.
even if you emulate it up the wazoo, I think perhaps the saving grace is if you get it right for one core, you've got it right for 128 cores.
Yes, as long
I
as you get
guess.
your whole interconnect right as well.
Yeah, actually, going through this and looking back on what you guys have written, I realized we didn't speak much about the interconnect
Oh, that's a
with these
complex topic.
guys.
Yeah.
Yeah. Well,
Because I mean, ARM obviously has their CI 600 stuff, and a lot of people like to run their own. Um, there are lots of different IP options, and it's not entirely clear which IP these guys are using. And there's some news
Or
about that
they've
you can go
designed their
read. But we
own.
won't touch on it here. Yeah.
At a high
So
level, it's a very large mesh. It runs at half clock. It's a lot like ARM or Intel's mesh
well, doesn't
architectures.
it run at half clock only over 4 gigahertz?
That's the funny thing too, right? So if you're
uh,
running at 3 gigahertz and running a mesh at 3 gigahertz, I think one of our friends, Titanic, right, has run a mesh overclocked at about 3 gigahertz, and it kind
And
of
that
power
I
draw.
think was
Yeah,
like 300 watts just in mesh power. Nothing
yeah.
else. Just the
If we
mesh
look
was
around a bit,
ridiculous.
if we look at what Ampere Ultra is clocking your mesh to, it's like what 2 gigahertz or something.
It's two
it's
gigahertz, and it's much smaller than this is.
Right.
I think a good way to translate this is running your memory controller at a 2-to-1 divider. Once your memory frequency goes up too high, right?
Yeah.
Yeah.
And even
It's
at that
that
two
sort
to
of
one
thing.
divider, you're still looking at
Yeah.
very high mesh clocks, higher than what most people are willing to clock their meshes up to.
I mean, we're already seeing with the AMD's Infinity Fabric takes so much power of that chip, power that you can't use on the cores,
Right.
right? So if you're saying not, so if we take the headline SKU, 950 watts,
Hmm.
128 cores. If you consider the mesh as 0, that limits 8 watts per core,
Right.
about that, or just under.
And that's already like
And
under
then
what a
At 5
desktop
points,
CPU will pull.
yeah, and then you're not even
but
talking about I/O power, which can
what,
not
so
uncore power, like I/O power for the DRAM controllers and the PCIe stuff.
I think my point is, if you look at, say, AMD's top CPUs, they run about 20 watts per core. Intel's can go north of 40 at
Right.
5.2 gigahertz. Now you're telling me you can get a core to run at 5.7 gigahertz for less than 8 watts?
Well, you're ditching the really, really good branch predictors that Intel and AMD have. You're ditching most
Yep.
of the out of order hardware. Maybe they have a very small amount of it, but you're also adding in these vector units that give you like
Mm.
twice or actually more than twice the throughput, and you're saying that you can run it there.
And you're hoping it doesn't do local brownouts as well.
Well, not just that, also your temperature, like just hot spotting, is going to be insane on this
Yeah.
because you're trying to run
950
that
watts.
950 watts
boy.
through 500 square millimeters. Your actual vector, your vector unit is going to be what, like maybe 1 millimeter per core, if I'm being really generous here.
Yeah, we've
And
actually
that's what's
like
going to be
cropped
eating a
out.
ton of power.
If we
Like,
crop out their die renderings and like look at the cores, and it's just like how the heck are you fitting that vector unit on there? But yeah, go ahead.
yeah, well, not just how are you fitting
May-
it, how are you cooling it?
Yeah, because part of your core is not going to be a vector unit. It's going to be a very
Yeah.
small part.
Yeah.
Okay, okay. Let me pitch you this. I'm not. Are you guys familiar with GraphCore?
Kind of.
No, I
I
feel
know
like
I know
I'm
of
not
them, but
too
not.
familiar with it.
Right. So their latest generation product is the same as their previous generation product, but instead they did wafer on wafer bonding. And on the underneath wafer, they used their deep trench capacitors. They put them on a separate wafer and bonded them that way. that gave them an extra 30% frequency with no additional power.
Oh, nice.
Interesting.
I've been wanting to do a video on it. It's called the Bow processor. It's named after the area in London called Bow, and the idea is that if you put enough of these together, you'll get what they call a good computer. So I kind of want to do a video on who wants a good computer. But yeah, the way they increase their frequency of that's TSMC 7 nanometer as well. So the fact that you don't need to put in or Intel with their SuperMIM capacitors, rather than actually having it in the design of your main die and having to do the routing with that, you actually have it on a separate die, deal with heterogeneous integration, and you get a frequency lift with no power lift. Your cost goes up because of packaging. We've only heard Rado speak about this processor in terms of a single monolithic. So
Yes.
And
Yeah.
using standard cell libraries at that.
Yeah.
yeah,
They're not using anything. They're not using custom transistors the way that Intel is hitting those high clock frequencies. They're using a lot of custom stuff on their CPUs.
Yeah. And
It's a small company.
is the AMD
Yeah.
for that matter. Like both of them are
AMD
using
seems to be using at least fewer library types.
fewer
But AMD
library
is also
types,
not clocking quite as high.
but I also guarantee you that they are still custom cells
Very
that AMD
likely.
themselves designed, but they're just using fewer of them, if that makes sense.
Yeah, it's very hard to tell because we're just
Yeah.
looking at die shots and guessing.
Just to wrap it up, I want to get your guys, sort of 15-second thoughts on, can Tachyum pull this off? Do you believe what they're saying?
I think it's possible, like given the thermal whatever targets and everything. As to actually succeeding, kind of.
Yeah, my inclination is that this is essentially a slightly less GPUified GPU for all intents and purposes. Because
It's this generation's Larrabee,
yeah, that's like
but
I
I have confidence that Rado will do something impressive, whether it hits these goals or not in the timeline. I am welcome to being pleasantly surprised.
yeah, like we said on one of the slides, on paper, theoretically, this may end up beating Epic or Xeon in single thread, like just standard CPU operations. But that's paper. In reality, actually trying to make that work is a much harder task.
Software ecosystem and all that jazz.
Yeah.
And
it gets really complicated.
And they're using software translation, which will always, unless they're doing so much better than Intel or AMD, and in which case they should just stop. Like, what have they been doing for 20 years? Right?
Right? And not just Intel and AMD, NVIDIA too.
Yeah.
It's
everyone.
with every processor you get a transmeta polyglot who does all the translation for you. That's what it is. Thank you guys for coming on to speak about the article. I highly suggest that everybody who's watching this video, if you've made it this far, congratulations. Check out the article on chipsandcheese.com. It goes into a lot more detail than we were able to put in here. Go follow them, go follow me, and again, thanks guys for your time.
Thank you.
Yeah, thank you.